What specific problem does the proposed method aim to solve in relation to the reliability of large language models, LLMs?
The proposed method aims to address the problem of LLMs producing incorrect predictions while lacking a mechanism to express uncertainty in their outputs. This issue is particularly critical in safety-sensitive applications, where users cannot gauge the reliability of the model's predictions due to the confident tone of the generated responses, even when they may be inaccurate. By augmenting LLM predictions with linguistic expressions of uncertainty, the method seeks to provide users with a clearer understanding of the likelihood that the model's predictions are accurate. This approach allows users to make informed decisions about whether to act on the information provided, request further clarification, or consult additional sources. Ultimately, the method enhances the utility of LLMs by ensuring that their outputs are well calibrated and more interpretable for end users.
How does the proposed method for generating uncertainty expressions work? Illustrate the key steps taken in the methodology, including the role of self-evaluation and isotonic regression.
The proposed method for generating uncertainty expressions involves several key steps. First, the model assesses its confidence in its predictions through a true-false self-evaluation task, where it determines the correctness of its own outputs. This self-evaluation yields confidence scores that are then calibrated using isotonic regression, applied to a small calibration dataset to ensure that the confidence levels are well aligned with actual prediction accuracy. Next, these calibrated confidence scores are mapped to linguistic expressions of uncertainty based on human perception of probability ranges. Finally, the uncertainty expressions are integrated with the model's predictions to create a fine-tuning dataset, which is used to train the model to consistently generate well-calibrated linguistic expressions of uncertainty in its outputs.
Can you provide a detailed example of how the proposed method generates a linguistic expression of uncertainty, including the confidence score mapping process?
The proposed method generates a linguistic expression of uncertainty by first assessing the model's confidence in its predictions through a true-false self-evaluation task, where the model determines the correctness of its own output. This confidence is quantified as a normalized probability assigned to the true token. Next, isotonic regression is applied to a small calibration set to refine these confidence scores, achieving near-perfect calibration. The calibrated confidence scores are then mapped to linguistic expressions of uncertainty based on a framework developed from human perception studies, which associate specific probability ranges with expressions like "it is unlikely" or "I am certain." Finally, these linguistic expressions are integrated with the model's predictions, resulting in outputs that convey both the answer and the associated uncertainty in a well-calibrated manner.
What significant benefits does the proposed approach offer over traditional numerical uncertainty estimation methods, particularly in the context of user interpretation?
The proposed approach offers several significant benefits over traditional numerical uncertainty estimation methods, particularly in terms of user interpretation. Firstly, linguistic expressions of uncertainty, such as "I am certain" or "it is highly unlikely," are more intuitive for users to understand compared to raw numerical probabilities like 90% or 10%. This enhances user comprehension and allows for easier integration of uncertainty into decision-making processes. Secondly, the linguistic expressions can be seamlessly integrated with the model's predictions, providing a more natural flow of information. Additionally, these expressions can indicate the source of uncertainty, whether it stems from the model's limitations or inherent ambiguity, which aids users in assessing the reliability of the information. Lastly, linguistic expressions are more adaptable for downstream applications, such as text-to-speech conversion, making them more versatile in user-facing applications.
How do the authors validate the effectiveness of their method? Describe the datasets used, metrics for performance evaluation, and any experimental design considerations.
The authors validate the effectiveness of their method by employing standard question-answering datasets, Trivia QA, Ambig QA, and Truthful QA. They utilize metrics such as accuracy, ACC, expected calibration error, ECE, and Breyer score to evaluate the performance of their models. The experimental design includes dividing the dataset into subsets for few-shot prompting, calibration, and training, ensuring that the uncertainty expressions align with the model's knowledge to avoid hallucinations. They also assess the calibration of the models on held-out test sets, specifically focusing on the calibration of linguistic expressions of uncertainty generated by the fine-tuned models. Additionally, they compared different methods of uncertainty augmentation, prefixed, postfixed, and interleaved, to determine which approach yields the best calibration results, finding that postfixed expressions lead to the lowest calibration error.
What were the main findings regarding calibration performance as reported in the results, and how do they compare across different model sizes and types?
The main findings regarding calibration performance indicate that pre-trained models exhibit better calibration than instruction-tuned models, with calibration improving as model sizes increase. Specifically, the Gemini 1.0 models demonstrated good calibration on self-evaluation tasks, particularly on the Trivia QA dataset, where post-processing confidence scores using isotonic regression significantly enhanced calibration. However, the models did not achieve satisfactory calibration on the truthful QA dataset, leading to its exclusion from the fine-tuning process. Additionally, the results showed that post-fixed uncertainty expressions yielded the lowest calibration error compared to prefixed or interleaved expressions, suggesting that the placement of uncertainty expressions affects the model's sampling distribution and overall calibration. Overall, these findings highlight the importance of model size and type in achieving well-calibrated predictions with linguistic expressions of uncertainty.